Okay, yeah, so hello, my name is Matjaž Gomilšek. Today I'll be talking about the Kondo effect in a quantum spin liquid. So this is a project that I did for most of my PhD, actually, and later on as well. The outline of my talk is as follows. So first I'll introduce the Kondo effect in general and quantum spin liquids, just so that we know what we're talking about. And then I'll introduce the material where we found a realization of this unusual quantum effect, and then some perspectives. So the Kondo effect is realized in metals as a peculiar minimum of resistivity, where instead of the resistivity of metals decreasing monotonically as the temperature is lowered, it sometimes increases at low temperatures. And it was realized that this is due to exchange scattering of itinerant electrons on magnetic impurities. So basically this second order process where an electron scatters off of a magnetic impurity by a spin flip in the intermediate state and then scatters off of that back to infinity. This process leads to a divergent contribution to resistivity at low temperatures, or at least naively divergent. It's not actually. This is due to the fact that this effect of extra magnetic scattering is non-perturbative. So at high temperatures, we can consider magnetic impurities as quasi-free, with just some weak coupling to the electrons, which scatter magnetically off of it. But at low temperatures, the electrons actually form a spin singlet with the magnetic impurity, transitioning it to a strongly coupled state, which is qualitatively different from the high temperature state. And this transition is non-perturbative. So the perturbative expansion fails around decay. This is called Kondo screening at low temperatures and leads to a peculiar appearance of Kondo resonance. So at the Fermi level, we get an increase in the local density of states due to this extra scattering of electrons on a magnetic impurity, which doesn't diverge, as perturbative expansions would tell you, but actually saturates to a finite value at low temperatures, below some characteristic Kondo scale, Kondo temperature scale. So this was observed in many materials, in many systems actually, so not just in metals, but also in quantum dots, quantum point contacts, topological insulators, graphene. Basically, anywhere we have a magnetic impurity embedded into a conductive host material, we get some version of the Kondo effect. This is due to the fact that the Hamiltonian is extremely simple. It's just basically the energy of free fermions plus an extra coupling term between the spin of the impurity and this small s. This is the spin of this itinerant host material. So these electrons around the impurity at the impurity site. So this local coupling of the impurity spin and the spin of the electrons produces this Kondo effect in general. Now the question is, could we get this also in electrical insulators? So where instead of having electrons as this conductive, so itinerant host, we would have something else. So for example, we would have for example, spin neutral, so charge neutral quasi-particles called spinons. So if so theory says that yes, we can get such an effect. So the reason is, in this Hamiltonian, there's no mention of the electrical charge of these electrons. So this Hamiltonian could just equally work for any kind of fermionic excitation, as long as it's coupled to the spin of the magnetic impurity via such a local simple term. And the electrical charge actually doesn't feature in this Hamiltonian at all, so we should get something similar anytime we have not just itinerant electrons, we have itinerant fermions of any kind. So one example is charge neutral spinons in spin liquids. But this was not observed experimentally because it's very hard to measure this kind of effects. Spin liquids are elusive in and of themselves to measure, and it's very much harder actually to discern what is the intrinsic spin liquid contribution and what's the impurity contribution. But we managed. So just to quickly introduce what a spin liquid is. So it occurs whenever we have a very frustrated spin system. So the basic element of frustration is such a triangle of free spins coupled antiferromagnetically. If we have that, for classical spin arrangements, we cannot ever satisfy all the local exchange interactions between the spins, any which way we arrange the classical spins. And this is called frustration. So we cannot minimize the classical energy of the system. This kind of frustration, if it's extensive, so it's not just a single spin triangle, but perhaps a lattice of triangles, or in this case a Kagome lattice of triangles, which is extremely frustrated, we can get a state that's actually a disordered and dynamic state of spins. So spins fluctuate dynamically even at 0 temperature because they have so many local degrees of freedom. So we can, for example, flip 6 spins in unit and leave the rest unchanged, and we get a new ground state with the same energy. So the ground state manifold can be highly degenerate. We can have many different configurations of spins equally good in energy. So the spin system can freely fluctuate between all of these arrangements of spins, at least classically. So we should get some kind of disordered and dynamic state at low temperatures. We have very large frustration and strong quantum effects, it turns out. So it's not enough just to have frustration. We also have to have some extra, usually some extra effect of quantum fluctuations, which leads actually to the ground state not being this kind of freely fluctuating spins that are classical. It's instead either a short range entangled or a long range entangled state, depending on whether the diametric excitations, the spin-ons, have a gap or they are gapless. So what happens actually is pairs of spins on a lattice form valence bonds, so singlets of 2 spins. And if there are short range singlets in a quantum superposition of possible arrangements, it's usually a gap system. If it's long range, it's usually a gapless system. So when I'm talking about a gap or a gapless system, I'm talking about excitations. So for a classical magnet, so an ordered magnet, the usual case with little frustration or classical spins, a single spin flip produces a localized excitation which can move only on its own. So it's a spin 1 excitation, but that has a sharp dispersion as a magnon usually. But in a spin liquid, if we break one valence bond, so one singlet on the lattice, we get actually 2 spins that are flipped, and they can move away one from the other at almost 0 energy cost. And because the spin flip fractionalizes into 2 spin 1/2 spin-on excitations, we call them, that move one away from the other almost freely, we get a continuum of possible excitation energy, so a continuum of scattering in neutron scattering experiments, for example, instead of a sharp magnon band. So we get from high frustration, we get excitations that are fractionalized magnetic excitations of spin 1/2 per each. So they are fermions. So we get magnetic fermionic excitations instead of magnons, which are bosons, to a good approximation. So not only that, the 2 fermionic excitations of these 2 spin-ons in a frustrated system are not completely free. They do have some small residual interaction, which is described by a gauge field. So that we get an emergent interaction between the spin-ons, because when they move around, they slightly perturb this covering of the basic lattice with singlets, and this costs a little bit of energy in the actual ground state superposition. And this small extra energetic term leads to an effective interaction between the spin-ons. They are not completely free. And this interaction is described by some gauge fields with some symmetry. So in a very analogous way to the way particle physics describes particles and gauge fields between them. So in this case, we get fermions with some emergent interaction between them. Okay, so this looks like a good starting point then to have maybe a Kondo effect with these kinds of spin-on quasi-particles instead as fermions instead of electrons as the fermions, providing the screening for the impurities. Okay, so but where could we find such a thing? So one example is zinc brochentite, which is relatively new Kagome antiferromagnet. It has a Kagome lattice of spins, so highly frustrated, and a certain fraction of the non-magnetic zinc sites are occupied by copper 2+. This is a planar structure, but some of these central sites are actually occupied by a magnetic atom. So this acts as an impurity on top of the Kagome lattice. We find that at low temperatures and low applied fields, it doesn't order. It has actually a quantum, it should be QCl, not QSL instead of QCl. So quantum spin liquid ground state below about 0.6 Kelvin with an extended regime at high temperatures of non-trivial behavior as well. And no magnetic order down to 21 millikelvin, despite the exchange interactions being about 80 Kelvin, so much higher, about 3,000 times higher. This is proved not just by bulk measurements, but also by local probe muon relaxation measurements, so no order and persistent dynamics. And if we apply a field to this kind of system, so we go from this regime, whereas at high temperatures we get this NMR 1 over T1 being almost linear in temperature, which is an indication of fermionic excitations, the same way that this linear term in the specific heat and a constant susceptibility are also indicating some kind of fermionic gapless excitation with a spin on Fermi surface. This is also characteristic of fermionic excitations with a Fermi surface. But below a certain critical temperature, we get a transition to a gapped kind of behavior with, again, no magnetic order actually forming, just a change in the excitation gap. So what happens is, if you apply a field, we go from a gapless spin-on metal type state, so where spin-ons behave like electrons in a metal, just with no charge, to a gapped spin-liquid state, depending on the field. And the gap that opens is actually proportional to the critical temperature. And this proportionality constant is about 3.9, which is very close to the BCS value of 3.53. So theory also predicts this kind of effect, and it says that it occurs due to spin-on pairing instability in a magnetic field. So a magnetic field helps induce some extra gauge interactions between the spin-ons, which then act as a glue, forming singlets of, or triplets actually, of pairs of spin-ons. So this, in a similar way to the way we have a superconductor forming out of pairs of electrons forming a Cooper pair, here we have pairs of spin-ons forming a spin-on pair with a gap that's basically a BCS gap. So this could be, if this is a spin-on metal type behavior, this could be maybe termed a spin-on superconductor. So a magnetic type of superconductivity without electric charge. Everything else is more or less the same. But we also find a spin-on condo effect. So this is the thing that's new. That wasn't observed in any kind of material before. All the other, so the gapless behavior and spin-on pairing instability were observed in other materials as well, but this is the first material that shows a condo effect as well. That's clear. So we proceed by local probe measurements. With NMR, we are only sensitive to the intrinsic gamma spins, which just the way that the deuterium nuclei for NMR are coupled to the lattice, they don't see much of the impurity contribution. But muons, being far away from most spins, see all of them more or less the same. And we can prove that they're actually coupled not just to the Kagome spins, but also to the impurity magnetic moments. So we can measure, the actual magnetism of impurities via USR measurements. And what do we get? So this K, this night shift, is proportional to the susceptibility of the impurities. So the low temperature susceptibility of impurities actually saturates to a finite value, so a plateau, which could be expected for free impurities just saturating in an applied magnetic field. We had applied magnetic fields here from USR, which are not very terribly high, but they are there. This is not the case here, because the actual moment in this plateau is not the full copper moment. Even when normalized to a single impurity site, it's substantially reduced by a factor of 8, about 4 to 8. And it doesn't behave in a magnetic field the same way a free impurity susceptibility would behave. So the magnetization of the impurities is not constant in an applied magnetic field. It actually increases slightly with the magnetic field. So it's not actually a saturated impurity at all. It's just a plateau coming from something else. So, but we definitely know that the impurities are not themselves free. So they're not just saturating normally in a magnetic field. We could try a short-range coupled model of impurities where we have clusters of impurities, if they happen to be close to one another, forming perhaps singlets if they're in pairs, or maybe reducing their magnetic moment from 3 spin 1/2s to just a total moment of 1/2. If there are 3 of them, they cannot go lower than that due to quantum addition of spin. But even if we could assume that all the even-sized clusters of impurities had spin exactly 0, and all the odd-sized clusters had a minimal possible spin for an odd-sized cluster being 1/2, we would still get some residual magnetization per impurity, so residual spin per impurity, just if the impurities were distributed randomly, because some of the clusters are outsized. And this is described by this series. So the first term is the contribution from impurities that are free, so with no neighboring impurities. This is 1 minus the impurity concentration to the power of the number of neighbors an impurity has in the lattice of possible impurity sites. W3 is the probability of having a cluster of 3 impurities, like shown on the figure. W5 is for 5 impurities in a cluster, and so on. So we derived actually an exact lower bound for the minimal possible magnetization per impurity if the impurities are distributed randomly on a lattice and interact one with the other with any kind of interaction. It doesn't matter what the interaction type is. This is ideal reduction of spin due to impurity-impurity interactions. And if we simulate this for different types of impurity lattices, for example, for the triangle lattice of hexagon centers or the Kagome lattice, we get the following curves. So the minimal possible impurity value, magnetization, versus the concentration of impurities. And so what we proved is actually so that any model of spin of impurity only magnetism should have an average spin per impurity above the corresponding curve here. What experiment gives us actually is an impurity moment that's lower than any of the curves shown. This proves that it's impossible to reproduce such a huge reduction of the impurity spin by just random couplings between pairs of impurities. Basically, because the number of impurities that are alone, so there is much too large. So the impurity concentration in experiments is about 6 to 9%, and lots of impurities have no neighboring impurities, so it's impossible for them to reduce their moment by forming a singlet with the next impurity. So that gives us a confirmation that actually the impurities are not just coupled amongst themselves. They have to be coupled to the spin liquid, or possibly if they were long range coupled amongst themselves, but that would lead to a spin glass type behavior, which would have then kinks in specific heat magnetization, things like that. That's what one would expect for a randomly coupled lattice of long range coupled impurities. We see nothing like that. We only see smooth curves. So this way we prove that impurities must be coupled to the host spin liquid. Is this a Kondo type coupling? It cannot be for a gapped spin liquid, as that would lead to a reduction of the impurity magnetization as the temperature is lowered, or a direct type spin liquid, so direct cone type dispersion for the spin-ons, that would lead to a divergence at low temperatures. Instead, we see a plateau, which theory predicts should occur when you have a spin-on Fermi surface in the spin liquid. So spin-ons actually do behave like electrons in a metal, so with a finite Fermi surface. Then we get a plateau in the stability. And we could try our first guess. Maybe the gauge fields, so the interactions between the spin-ons are not important. Maybe this actually does behave just like a standard metallic Kondo effect with nothing else. And to a first approximation, it works surprisingly well, with only 2 fit parameters for the whole dependence. One is the impurity concentration, which comes out to the fit at 9%, whereas XRD and other experiments give us a range of 6 to 9%, so completely agreeing with the Kondo model fit. And we get the Kondo temperature of around 1 Kelvin for this transition to the low temperature plateau, whereas the Weiss temperature of impurities is 1.2 Kelvin, and Kondo theory predicts that the Weiss temperature and the Kondo temperature should be of the same order, so similar one to the other, and we see exactly that. So these are the only 2 free parameters in this. The curves are actually calculated from numerical renormalization group calculations with no other adjustable parameters. So this is actually a surprisingly good fit. And we can also observe the splitting of the Kondo resonance. So we said that on the Fermi surface we get an increase in the local density of states due to this Kondo effect of impurities coupled to some itinerant fermions. If we apply a magnetic field, this resonance Zeeman splits into 2 resonance peaks, and then the number, so the local density of states at the Fermi level decreases in a non-trivial way, non-Barlow type decrease. And this is a fingerprint of Kondo physics, actually, that this doesn't occur at 0 applied field, but only once we pass the width of the resonance. And we see exactly that in MuSR. So if we measure the local relaxation rate of muons, which measure the dynamics of impurities, we see a critical field where the behavior changes from one power law to another power law quite abruptly, actually. And if we plot the critical field for this splitting, we see that it's linear in applied, so linear, the temperature is linear in field or vice versa, which is exactly what one would expect from conduct theory. But critically, the field for the splitting at 0 temperature, the extrapolated value, is non-zero. So this only occurs if we have a strong coupling with some non-trivial condo coupling of the impurities. It wouldn't happen for normal Zeeman splitting, where you have a thin peak that splits immediately. We have to have a wide resonance so that it splits only above a finite applied field. And we see exactly that in intercrease with condo theory as well. So in this way we prove we have a condo effect.
So 5 minutes left.
As the itinerant host.
So Matjaž, 5 minutes left.
I mean, okay, thank you. So this is then the final phase diagram. So we have at low applied fields, we get a transition from weak condo coupling at high temperatures to strong coupling at low temperatures. Whereas at high applied fields, we also get a gapped spin liquid phase as well. Aside from this, the rest of the phase diagram where the spin liquid is gapless with itinerant fermionic-like spinons with a spin-on Fermi surface. And this is just an illustration of how this might look like. So if we imagine at a high temperature, we get the blue balls are impurity so impurities. Red balls are spinons. At high temperatures, the impurities are quasi-free, so not screened by the spinons, whereas if the temperature is lowered, they get progressively more and more screened by the spinons forming a singlet state with the impurity. So in a way, concentrating around the impurities would be the real space picture of this screening them at low temperatures. And this is a highly non-trivial effect. Let me just quickly mention the other things we see from this. So the standard condo effect fit is very good with just 2 free parameters, but it's not really perfect. So the question becomes, what is the perturbation that makes this seem a bit systematically offset? So the points are the experimental values, whereas the blue curve is theory. It agrees within error bars with just 2 free parameters, but still the slope seems systematically a bit off. So we tried a number of perturbations, which I don't want to go into detail about, but we calculated all of them using numerical normalization group and DMFT approaches. So either we include a narrow spin-on bandwidth as a perturbation, which doesn't give good agreement, or we include the G factor for the spin-ons, or a non-constant spin-on density of states across the Fermi level instead of a constant, or potential scattering of spin-ons of the impurity, or even anisotropic condo couplings, so where you get XXZ type anisotropies in the coupling between the impurity spin and the itinerant spin-ons, or even partial gap opening in the spin-on spectrum, either a hard gap or a BCS gap, which gives actually an opposite effect in field to what we need. And it's also not the effect of a finite impurity concentration, so it's not a dilute condo lattice of impurities, simply because the impurity concentration is too low. You would need about 50% impurity concentration to see any good effect. This is because all of these effects are actually too small, because the condo effect is a universal feature. It comes from the normalization group, and it is very hard to break this universality. All of these things I mentioned above do break universality of the condo effect, but only slightly. It's a very small perturbation. There are only 2 things that could potentially explain it. So the low field, so the field dependence could be explained by an anomalously high impurity G factor, which fails at high temperatures to describe the data. The only thing that does actually completely describe everything is if we include a renormalization of the spin-on G factor to a negative value, which might seem strange, because electrons usually have a positive G factor of 2, whereas spin-ons, they can couple strongly to gauge fields. So when we apply a magnetic field, the magnetic field induces some distribution of gauge fields inside the spin liquid, and that can renormalize the G factors of the excitation, so the spin-ons. This is actually a known effect from theory, and it is possible to have a negative value of the G factor from that as well. But this is not conclusive, this is an empirical fit, actually. But it seems that we might have observed as well the signature of gauge fields as well, not just spin on Fermi surface, but also the gauge fields coupling the spin-ons between themselves. For the evidence for the gauge fields is actually the small power law at low applied fields in muons. It should be constant for a pure Kondo effect, but it's 0.2 in power due to gauge fields. This Coringa relation at high temperatures from NMR is 0.8 instead of 1 in power, again due to the gauge fields. And also the spin-on pairing instability itself is not possible without gauge fields. There has to be some glue between the spin-ons so that they form a triplet pair instead of having purely free spin-ons. So perspectives, this is almost the last slide. So we could use this effect to identify elusive quantum spin liquid states in general in other materials as well. If we could decouple the magnetic contribution from impurities from that of the host spin liquid, which we did successfully in zinc brochentite, but it should be possible as well in others. And we saw that it's extremely powerful for doing that. We saw the effect of gauge fields and the spin on Fermi surface. So these are highly non-trivial things to get otherwise. And we could also potentially as well manipulate the quantum spin liquid state via impurities. So we could apply a magnetic field to the impurities and induce a local change in the spin liquid. Or if the impurities are dense enough, maybe a global change as well, possibly even in the topology of the spin liquid. So this is also predicted by theory that it should happen, for example, in the cation spin liquid. If we have a cation spin liquid with a Kondo impurity, if we apply different magnetic fields, we could transition between different regimes of the cation spin liquid through this interaction through the impurity. So, in summary, we observed the spin-on Kondo effect. So this is the first time we saw a Kondo effect with charged neutral quasi-particles, in this case spin-ons in the spin liquid. We detected spin liquid gauge fields potentially in this through this effect, and this gives us a new way to study and also control spin liquids in general. At the end, I'd just like to acknowledge my collaborators. So mostly this work was done with Andrei Zorko, Jožef Stefanis did it, Matej Prega, Martin Klanšek, and Rob Žitko for the numerical calculations, as well as other collaborators for the experiment. And yeah, thank you. If you have any questions, please.
Meanwhile, I can ask you quickly, do you have some educated guess, some other system when you can observe a similar effect? Because in this case you show the zinc brochentite, but can you, I mean, try to guess which kind of system might be suitable for observing similar effect? I know it's not easy, there are too many conditions to be fulfilled.
It's not easy. So the thing that helped us in this case was the strong renormalization of the spin of the impurities. If the renormalization was weaker, it would be hard to discern that from other models. But in principle, so we should get something similar in Herbert-Smithite as well, which is extremely famous. It's a quantum spin liquid and also extremely controversial due to many different interpretations of the spectrum. But there we saw from electron spin resonance already some indications of strong coupling between the spin of the magnetic impurity and the host spin liquid. We saw a broadening of ESR peaks due to that, and also two types of spin liquid impurities in that, not just a single type. One was quasi-free, the other was strongly coupled to the spin liquid state. But it's still very early days to say that this is truly a Kondo effect, not some other type of broadening or something like that. So that was one case, and also another possibility would be if we could induce impurities in some kind of very clean material. For example, in cation spin liquids, this is a system that's getting more and more under control experimentally and theoretically. Perhaps if we could introduce some kind of local impurities, we could measure some effect from that as well. Because there's a lot of theory actually from sound effects in cation spin liquids.
Many thanks.